tomorrow will be better. In this question on the board, we are told that a sports car denoted as so is traveling at an initial velocity US collides with a stationary truck denoted as so, and at the end of the collision, both cars get stuck together and they travel with a joint velocity denoted as uj for a further 3 meters before coming to a rest. Now the question says find the initial velocity of the sports car. Follow me dear friends. Solution. In this question again, we've been given the coefficient of dynamic friction, which is so. Already this brings to mind the presence of friction force. Okay, so of course this is linear momentum in action, so we have to apply the law of conservation of linear momentum, according to which the mass of the sports car times its initial velocity plus the mass of the truck times its initial velocity should give us the joint velocity after the collision times the sum of their masses as so. Okay, but we know that this quantity here is going to boil down to zero because the truck was stationary. In other words, from this equation we're going to have that the initial velocity of the sports car, which is our center of interest, is going to be given by the joint velocity times the sum of the masses divided by the mass of the sports car. We can call this equation 1. Notice here that we don't have the joint velocity, which is the velocity after the collision, and we need to obtain it. Now to do this, we will have to divide our motion into two phases, the collision phase proper and then the post-collision phase. At this point, if you haven't subscribed yet, subscribe to my YouTube channel to have better updates. And if you have any particular concerns, you can email, you can write it in the comment section, and you can do a special session for you. Okay, so I want us to bear in mind one thing. In order for us to have this, we're going to apply a new principle here, or a new theorem, which is that of work kinetic energy. According to this theorem, the work done by any force can be equal to the change in the kinetic energy of the object on which it acts. Now, where is all of this coming from? We already know that for this joint object to come to a stop here, there's a friction force. Now, this friction force does some work to slow down the motion of this joint object. It is this work which this friction force does, which we're going to equate to the change in the kinetic energy of this object here. Already, we can put a minus sign here. Why? Because what is doing this work is an opposing force, which is friction force. So it takes a negative sign. Now, what is going to be the change in the kinetic energy of this joint mass? It's going to be equal to the final kinetic energy minus the initial kinetic energy. Of course, the final kinetic energy will be zero. Why? This is simply because we know that at the end of the day, the final velocity is zero, and kinetic energy is dependent on velocity. At the end of the day, we just have that all of this will boil down to the initial kinetic energy of this object, which is nothing else but negative half of the mass of the stationary car and the train on the truck, times the joint velocity all squared. Okay. Now, what about this term to the left? We know that work done is equal to a force times a distance, but in this case, the force here is the friction force, which is really not labeled anywhere here. We don't have any value here labeled friction force, but we can obtain it using our value of mu d, which is going to be equal to the normal reaction times mu d. Now, since we are on a flat horizontal surface, the normal reaction force is just simply going to be the weight of the joint object. Okay, so again we can further do this: m of sports car and truck, g for this times mu d. So at the end of the day, the work done is going to be equal to the mass of truck and sports car, the gravitational acceleration, mu d times the distance traveled. Okay. Now notice that there's a negative to the left and there's also a negative to the right. So both negatives are going to fall off. Okay, so let us now apply this. This means that work is going to be equal to kinetic energy initial. And the implication of this is what is NST times G times mu D, and here times the distance moved. This should be equal to half mass ST U joint or square. What are we looking for in all of this? We are looking for the joint velocity of these two cars. Okay, so this falls off with this, and if you correctly make UG the subject, this is going to be equal to the square root of 2 times G times mu D, and then times, or let me just replace them by the values. We're going to have here times, okay, times G times mu D, and then times D. So this will be equal to the square root of 2 times 9.8 times 0.8, it was given, and then times the distance 3. If you correctly bunch, this should be able to give you 6.9 meters per second. Now we are not done. This was not the object, this was not the question. The question was to find US, which is the initial velocity of the sports car. So how do we get US from here? We just put the value, so we will say put U joint in equation 1. Where is equation 1? This is equation 1 right here, okay? So we will have that US is going to be equal to U joint 6.9 times the sum of their masses, that of the sports car first 950 plus that of the truck 2,200 all over 950. And if you correctly punch, this is going to be equal to 22 point, I think roughly 7 meters per second. And this is the velocity of the sports car. If this video was useful to you guys, share it to other friends, because tomorrow will certainly be there.